Hello, and welcome to this presentation, Understanding Zero Span. In this short presentation, we'll explain zero span mode on a spectrum analyzer, as well as how zero span measurements can be used for different applications. If you're unfamiliar with spectrum analyzers in general, it would be a good idea to watch the presentation, Understanding Basic Spectrum Analyzer Operation, before continuing with this presentation. Let's start with a brief explanation of what we mean by zero span. A traditional heterodyne or swept spectrum analyzer measures spectrum by effectively sweeping a resolution bandwidth filter across a frequency span, measuring and displaying the power along the way. If, however, we set the analyzer span to 0, the resolution bandwidth filter stays parked on a single frequency. The analyzer now displays power within the stationary resolution bandwidth filter as a function of time. If zero span reminds you of an oscilloscope, there's a good reason why. Both produce amplitude versus time results. However, there are two important distinctions to keep in mind. First, remember that oscilloscopes typically measure voltage versus time on a linear scale. But with a spectrum analyzer in zero span mode, we're measuring power versus time, usually on a log scale. A simple sinusoidal signal sometimes looks different when viewed on an oscilloscope and on a spectrum analyzer in zero span mode. Changing the spectrum analyzer vertical scale to a linear scale instead of the normal log scale will usually produce a more normal-looking sinusoid. Remember, too, that in general, a spectrum analyzer will have a higher dynamic range than an oscilloscope, but the oscilloscope will have higher bandwidth. These considerations often determine the choice of zero span versus oscilloscope for a given measurement application. When configuring zero span on a spectrum analyzer, we supply the center frequency and, of course, set the span to 0. We also need to decide on values for resolution bandwidth and video bandwidth. Resolution bandwidth should be set at least as wide as the measured signal, preferably a little bit wider. Using a resolution bandwidth that's too narrow for the signal of interest means that we're only measuring part of the signal, and this could lead to inaccurate results. Too narrow of a resolution bandwidth can also lead to distortion of a power versus time trace. We'll look at this more closely later in the presentation. When it comes to video bandwidth, a good rule of thumb is that video bandwidth should be wider than the resolution bandwidth, since this helps to avoid excessive smoothing of the signal. Note, however, that in most cases, having an incorrect resolution bandwidth is a much more serious problem than having an incorrect video bandwidth. There are many different applications for zero span mode. Some of the more mundane uses are for audio demodulation, or deciding the proper trigger level for a gated measurement. Zero span is frequently used for measuring power, such as when making channel power measurements, or measurements of wideband noise. And probably the most common application of zero span mode is measuring the envelope of pulsed or other time-varying signals. Let's take a look at the use of zero span for audio demodulation, channel power, and pulsed or time-varying signals. A common marker function in spectrum analyzers is AM and FM audio demodulation, whereby we can listen to analog modulated signals. The procedure is fairly universal. We place a marker on the signal of interest, change the marker function to demodulation, choose AM or FM, and select an appropriate resolution bandwidth. The resolution bandwidth should be wider than the signal and any sidebands to avoid distorted audio. For broadcast FM radio, this is usually 300 kHz, and for narrowband FM transmitters, we normally use a 30 kHz resolution bandwidth. In normal swept mode, we would also need to set the demodulation time. In other words, how long does our sweep pause and demodulate the signal before resuming the sweep? In zero span mode, however, the resolution bandwidth is not sweeping, so demodulation time is essentially infinite, and we get an uninterrupted audio output. Another way we can use zero span is to make channel power measurements. We set the analyzer to the center frequency of the channel, enter zero span mode, and select our resolution bandwidth. The analyzer measures the power within the resolution bandwidth, and channel power is shown as a line on our display. Power can be read off manually, or using a marker. And remember that because we're measuring power, we need to use the RMS detector. Measurements of power versus time are frequently used for pulse signals, such as those found in radar, or for other time-varying signals, such as the bursted or time-division duplex signals that are used in some wireless communication standards. Zero span allows us to see power over time, or to observe the envelope of the signal. In almost all cases, some type of trigger must be defined in order to get a stable signal, or to freeze the time-varying signal on the screen. The most common way to trigger on signals in zero-span mode is using a video trigger. A video trigger defines a level which, when crossed, causes the instrument to trigger. Another common method is using an externally supplied trigger signal. Remember that pulse signals, especially those with steep edges and rapid rise times, have relatively wide spectral widths. In order to faithfully represent these pulses in the time domain using zero-span, the resolution bandwidth must be set wide enough to capture a significant portion of the pulse signal's power. Too small of a resolution bandwidth leads to pulse edge rounding, and eventually to distortion of the pulse envelope. In summary, zero-span fixes a resolution bandwidth at a given frequency instead of sweeping it across a span. When zero-span is enabled, the analyzer displays power versus time within the resolution bandwidth. This is similar to how an oscilloscope displays information, but remember that scopes typically display voltage, not power, as a function of time. Zero-span can be used for many different applications, such as audio demodulation, channel power measurements, and analyzing or measuring the envelope of pulsed or other time-varying signals. And don't forget that using the proper resolution bandwidth is of critical importance in any type of zero-span application. This concludes our presentation, Understanding Zero-Span. Thanks for watching.